Welcome to our applied lesson with RStudio. In this lesson, we perform historical simulation using some real data. We will consider a small data set, but we will see how we can generate our scenarios, and on the basis of the scenarios, how we can get our loss distribution from which we compute the value at risk, the expected shortfall, the stressed value at risk, and so on. Okay, so we will see that with a step-by-step procedure. Obviously, you can imagine that in a large bank, everything is more or less automized. You don't necessarily use R, you can use other languages. Unfortunately, very often they use Excel. We will do that with R, and we will try to see the different steps. In this lesson, you will also find some exercises that I suggest you to try to solve because they are very important to better understand some of the things that we have been saying together in the last lessons. Okay, so in this lesson we perform the historical simulation for market risk using some real data that are contained in the historical.csv file. This is a comma-separated dataset in which the separator is the semicolon. Okay, now what we can do, we can just read the dataset, and if we have a look at the dataset, we can see that it contains what? It contains a certain number of days. You can imagine 501 because we want to generate the standard 500 scenarios, and for the different days, what do we have? We have the value of four important indexes: the Dow Jones Industrial Average, we have the FTSE 100, QRM, the Nikkei, and because these are the constituents of our portfolio. The value of our portfolio today is $10 million, and the quantities that you see here on the screen are already all expressed in dollars. This is very important because you can imagine that CAC count, for example, is expressed typically in euros. So you cannot compare apples and pears, so you have to choose one currency. It's up to you. Here we have used the dollar, but we can do the same with euros. But what is important is that everything is expressed in the same currency. So it means that if you consider the CAC count, if you consider the FTSE, you have to take the exchange rate of that date and transform everything with respect to the exchange rate into the currency of your choice. Now, our portfolio is worth $10 million today, and the composition of the portfolio is the following. We have $4 million for what concerns the investment in the Dow Jones, $3 million for what concerns the investment in the FTSE, $1 million for what concerns the investment in the CAC 40, and $2 million for what concerns the investment in the Nikkei. Okay? Now, what we want to do is to generate 500 possible values of our portfolio tomorrow on the basis of the last 501 observations that we have available in our dataset. Now, how can we do that? We can generate a new dataset that we call scenario, in which we just create the values of the different indices according to the daily variations that we have observed in the different days. So we consider, for example, under the first scenario, the variation between this value and this value for what concerns the Dow Jones, and this value for what concerns the CAC 40. And this is this part of our code. And we then multiply this variation for the value of the different indices today, and today is day n, that corresponds to our last day in the dataset, which is day 500. Okay, so if we do that, what we get is the following dataset, in which for the different scenarios we have the possible values of our different indices generated according to our historical data, okay, using the formula that we have considered together. Now, what we want to do is now to verify what will be possibly the value of our portfolio tomorrow on the basis of the different scenarios that we have generated, okay? So we create a counter for the number of the scenarios, and then the portfolio, the new values of the portfolio, the new 500 values according to the 500 scenarios of our portfolio are obtained in the following way. Now, we express the amounts we have today of the different indices, 4 million for the Dow Jones, 3 million for the FTSE, and so on, in thousands, okay? So 4 million is 4,000 for us, and we multiply this quantity here with respect to the different scenarios, rescaled by the value of today, obviously, because we want to see with respect to the daily variations. Now, if we do that, we see that according to our scenarios, under the first scenario, the value of our portfolio tomorrow will no longer be 10 million, but something less. The same with respect to the second, the third, but for example, under the fourth, there will be an increase in the value of our portfolio. So we expect 3 losses in the first 3 scenarios and a profit in the fourth. And in fact, if we compute the possible losses, what we can compare is the value of our portfolio today, 10 million, again expressed in thousands, with respect to the value of the portfolio under the different scenarios. What we get is a new variable loss that contains a loss of 7,000, a loss of 38,000, a loss of 78,000, a profit of 87,000, and so on, okay, for the different scenarios. Now I can combine all the quantities that we have generated in just one data set that I called scenario, okay? So in this data set now we have the different scenarios, the different possible values of the indexes, the possible value of our portfolio under that scenario, and the corresponding loss. Remember, losses are positive and profits are negative. Now, we attach the scenario so that we can just use the name of the columns without using the dollar notation. And one thing that I ask you to check is, since it's an assumption that we will do, for example, under the model building, and it's typically a wrong assumption, I want to show you that if we assume our losses to be normally distributed, probably we are doing something not completely correct. In fact, if we have a look at the histogram of the losses, we see that there is some symmetry, but we see that probably the mass we have on the loss side is a little bit higher, but still acceptable. So let's say that if we are not extremely picky, we still can accept the symmetry, the bell-shaped behavior of the distribution. This is somehow confirmed by the descriptive statistics, but also here, even if the magnitude is not particularly large, we can see that there is not exact symmetry because of the fact that the median and the mean are not the same value, yet they are close enough in relative terms. But what is important is that if we consider the normal QQ plot, so if we compare our empirical data against the theoretical quantiles of a normal distribution, what we get is that in the tails we have problems. And in fact, the problem, when you assume normality for quantities like the returns, losses, and so on, is never in the bulk, is always in the tails. So one exercise that I ask you to do is to verify if using tests for normality, the Kolmogorov-Smirnov, the Jacques-Berat, what you want, or using EVT and looking at the tail parameters, if you can reject or not the null hypothesis that our loss data are normally distributed. You will see that in reality you have to somehow reject the null hypothesis if you want to be precise. And why? Because the tails of this possibly bell-shaped distribution are essentially different from the tails we would expect under a normal distribution. They are thicker, okay? And that's why assuming normality every time, it's a problem. Unfortunately, we know that, yet a lot of people like to assume normality, even if it makes no particular sense. And not assuming normality does not mean that you have to assume some strange type of distribution. Sometimes it is even sufficient to assume a t. So my point is, why do you insist in assuming normality when you have other simple alternatives that work much better? The answer is nobody knows. We are just probably a lazy type of animals. Now, what we can do is the following. Imagine that we are interested in computing the 95 and the 99% valid risk for our losses. There are different ways in which we can do that. I want to show you a very basic and trivial way and something relatively fancier. Now, the easy way is the following. We can always sort all our losses from the worst, so the highest loss, remember that for us losses are positive, to the best, that is the lowest loss, that is possibly a profit, so a negative quantity. Now, if we do that, we have that our data can be sorted in this way, and we find that the worst scenario for us is scenario 494, the second worst is scenario 292, and so on. Under the worst scenario, we have a loss of almost $500,000 with respect to our portfolio. Now, since we want to compute the 95% valid risk, the 95% valid risk is that value such that 95% of the observations are smaller and only 5% are larger or equal to. Now, a very trivial way of computing this, once we have ordered our losses, is just to take the top 5% of the observations. So 5% of 500 is 25, so our 95% valid risk will be observation 95, since the losses have been ordered, okay, so it's very important. This value is 160,000, okay? If you want the 99%, what you take the top 1%, so 1% of 500 is 5, and the value that you get is obviously larger. If you want to compute the expected shortfall, then it is very simple. What you just have to do is to compute the mean of all the observations above the valid risk. So for the 99% confidence level, we take the mean of the top 5 observations. And this value is 369,000. Please notice it's trivial to observe that the expected shortfall is always larger than equal to the corresponding VaR level. Actually, it can only be equal to the VaR level in case of a degenerative distribution that puts a mass on a specific value, otherwise it is always strictly larger. So let's say that virtually it is always strictly larger. Now, as you remember probably from our previous class, we have introduced the stressed VaR. What is the stressed VaR? The stressed VaR in the Basel 2.5 and then 3 framework is the valid risk computed on the worst scenarios. Typically, the worst scenarios are the worst 50% of the scenarios. So what we compute when we consider the 95% stressed VaR is the 95% valid risk of the worst 50% of the scenarios. So if you order the scenarios from the worst to the best, actually the 95% valid risk would correspond to the 97.5% valid risk of the original data set. Why? Because we are taking the value such that 5% of the observations are larger, but we are taking the 5% of half of the observations. So the top 2.5% with respect to the original data. So it means that we have to take the top 12.5 observation. Now it is not possible to take 12.5 observations. We have to round to either 12 or 13. If you want to be conservative, you can pick the biggest one. So if you do that, the stressed VaR at the 95% confidence level is 185,000. And as obvious, this value is larger than the original 95% valid risk, because we are just focusing on the worst scenarios, those generated the worst losses for us. Now, all these quantities can clearly be recomputed in a more fancy way. One way is, for example, to use the quantile function that allows us to compute the empirical quantiles given a given data set. Okay, now the quantile function, I suggest you to type $quantile to read all the different aspects of this function. But you can select up to 9 different ways of computing quantiles. In the statistical literature, there are different algorithms for interpolation of the quantile function, and choosing one algorithm or the other can give slightly different values. Of the different 9 types, unless you have very problematic data set that are discontinuous and so on, I typically suggest to use type 6. Now, if you want, you can compute the 95% valid risk by typing quantile scenario. We take column 7, that is the column that corresponds to losses, and then we say that we want the type 6. So we ask our code to compute for us the valid risk at the 95% confidence level, and what we get is a value of 160,000, which is actually, you see, very close to what we have computed using our manual procedure. Okay, it's not exactly the same because in the quantile function, nevertheless, you interpolate, okay? And this becomes quite evident, for example, when you try to compute the stressed VaR, because in the stressed VaR situation, we have to pick, in theory, observation 12.5, which is not possible, so either we choose 12 or 13, while the interpolation procedure will actually try to find out this actual observation 12.5. If you want to compute the 99% valid risk, always using the quantile function, what we get is a value of 276, and this value is again close to the one that we have computed manually. Okay, so let's say that if we round, as you typically do, so we are not really interested in decimals in these kind of things, if you round, the values are definitely comparable. Now, what I ask you to do, and I will discuss with you the results later in our next live class, and also in the other exercises that we will consider together in the future classes, is to solve these 2 exercises that you see in the file. The first one asks you to apply extreme value theory to the loss distribution above, the same distribution for which I asked you in exercise 1 to verify normality. So if you want, you can combine the 2 exercises. And once you have used extreme value theory and you can actually model the tail of the distribution in a more appropriate way, what I ask you to do is to compute, as we have done in other situations, the valid risk and the expected shortfall, for example, at 99% confidence level, and compare these values that you get with those that you get empirically, like, for example, these ones that we have just computed. And then try to see if using EVT gives you values that are larger, smaller, or more or less the same as those that you get empirically. You should find something interesting. And the third exercise is just a very basic exercise. In the theoretical class, we have seen that if we want, we can extend the historical simulation by introducing weights, or that are, for example, those in terms of the lambda parameter. We have seen the ones in volatility. And what I ask you to do is to try to perform again all the analysis, but now you weight the scenarios using a lambda of 0.995, which is a lambda that slightly gives more weights to the observations that are closer to us in terms of time. So the observations for 500, 499, and so on with respect to observation 0, 1, 2, 3. Once you have done that, you will see that your values obviously change, and then one can start thinking about the problem of historical bias, but we will see all these kind of things later on. Okay, so that was it. Thank you for your attention, and please spend some time on the exercises, because it's very important to make your hands dirt with exercises, with data, if you want to really learn how to play with risk management in practice. Just waiting for my solution in the live class is not the best way to learn. Okay, so try to solve them, and we will be back in the next days.